Now we are going to discuss some more concepts that describe motion in a straight line, and what we will be doing is we will be continuing with the example on straight line motion that we took up in the previous video. Now if you recall, in that example, this is the straight line along which motion is taking place. This towards right is the positive x direction, and this towards the left is the negative x-axis direction. The object started moving at the initial time. That's when we started observing the motion, time equal to 0. It started at x0, that was the initial position. Then at time t1, the object was observed at position x1. It then stopped for a moment, it stops and then reverses direction and is observed at x2 when time is t2. Now what we are going to do is we are going to draw a graph that depicts this motion, and at this stage what we'll do is we'll have a first look at what we call the position versus time graph for this particular motion. Now we are not really aware of what was happening all throughout. We just know what's happening at time equal to 0, what's happening at time equal to t1, and so on. So in between, what was happening is now depicted in this graph. Now the graph can give you the position of the moving particle at any point of time. And later on as well, you will notice that we use these graphs quite a bit to develop a good understanding of what's happening in a given motion. Now this is our first introduction to the graphs that we use for studying motion. This graph is giving the position x at all different points of time. For instance, at this particular time, if you draw a vertical line, the point of intersection here gives us the position x at that particular instant. So at time t1, the position is x1, time t2, the position is x2, and at time 0, the position was x0. So this is the position versus time graph representing this particular motion. In the previous video, we discussed about the distance and displacement in this motion in various intervals of time, and we will be referring to those magnitudes of distance and displacement once again now. To start with now, we are defining a new concept which we call average velocity during this motion. Now, average velocity during any given interval of time is the displacement during that interval divided by the time consumed in that interval of time. So the total displacement undergone by the moving object divided by the time of the interval gives us average velocity during that interval. Now if we were to look at average velocities during various intervals here, we'll be looking at 3 different intervals. The first one is from time 0 to time t1, the second one is from time t1 to time t2, and the third one is from time 0 to time t2. Now for the first interval from time 0 to time t1, we are looking for the average velocity. So from time 0 to time t1, the displacement is x1 minus x0. So that displacement x1 minus x0 divided by the interval duration that is time t1, gives us the average velocity during this interval. So it turns out to be x1 minus x0 by t1. Now let's have a look at the next interval from time t1 to time t2. Now from time t1 to time t2, the particle has come from here to here. The final position minus the initial position gives us the displacement. So x2 minus x1 is the displacement. We divide that by the time duration of the interval. Now when the particle was here, the stopwatch was showing time t1, and when the particle is here, the stopwatch is showing time t2, and therefore the time taken from here to here will be t2 minus t1, and this therefore gives us the average velocity from time t1 to time t2. Let's look at the entire motion now for the third interval from time equal to 0 to time equal to t2. Now from time equal to 0 to time equal to t2, the displacement will be the final position x2 minus the initial position. So x2 minus x0 is the displacement, and the total time taken from this position to this position will be t2 minus 0. And therefore the average velocity is x2 minus x0 by t2 minus 0. Now for the same motion, let's also define another concept, and this time we define average speed. Now the average speed during a given during a given interval in a motion is the total displacement during that motion divided by the time consumed in that time interval. Now to understand this a little better, let's take up the examples for average speed for the same three intervals. Now for the first interval, that is from time equal to 0 to time equal to t1, from here to here, the distance traveled is this length of path, which is magnitude of x1 minus x0. This is x1 minus x0 divided by the time. Now you will notice that the average speed here has the same magnitude as the average velocity. The only difference being that the average velocity will be depicted with a positive sign here, whereas with average speed we do not bother with the sign. The sign here shows the direction. There is no meaning of direction here. Average speed is a scalar quantity, does not have a direction. It's a scalar by a scalar, so it's a scalar quantity. Now for the second interval from time equal to t1 to time equal to t2, from t1 to t2 the particle moves from here to here, and the length of the path is the magnitude of x2 minus x1. The time duration of the interval is from from t1 to t2, and that therefore is t2 minus t1. So we divide this displacement by this time and we get average speed for this interval. Now the average velocity during this interval was a negative quantity because x2 was less than x1, and the direction of the average velocity was also towards left, that is the negative x direction. So this was supposed to be negative, and we were getting a negative value using this calculation. With speed there is no meaning of negative sign, so we have a mod here, and therefore we get the magnitude of average speed here as mod of x2 minus x1 by t2 minus t1. Let's move on and now discuss the entire motion from time equal to 0 to time equal to t1. Now for this motion, remember we are looking at total distance by total time. That's the average speed. Now for this motion, the distance is the length of this path plus the length of this path. Now what are those lengths? Mod of x1 minus x0 plus mod of x2 minus x1. Now remember, if you're calculating distance in any straight line motion scenario and there is a reversal in direction, there is a change in direction, then the distances before and after the direction change must be calculated separately and added. And so this way here we get the total distance and divide it by the time t2 minus 0, we get the average speed. Interestingly, you will notice that the average speed for this entire motion, which involves a reversal, which involves a change in direction, well, this average speed is going to be greater in magnitude than the average velocity. And that will always be the case whenever there is a reversal in motion direction. So when motion direction changes, average speed is greater than average velocity. Otherwise, if there is no change in direction of motion, the magnitude of average velocity and average speed will come out to be same. So that's it about average velocity and average speed, and we then move on to slightly more interesting, slightly different concept, and that's instantaneous velocity and instantaneous speed. Now, what are these two quantities? Now, imagine that I drive from my home to my workplace, which is 20 kilometers from my home, and I do this every day. And on a typical day, when there are no traffic jams, it usually takes me about 30 minutes to travel this 20 kilometer distance. Now, which tells me that the average speed with which I travel from home to my workplace, that average speed is 40 kilometer per hour. Now, if in half an hour I'm traveling 20 kilometer, then in 1 hour I'll be traveling 40, right? So in this particular commute from my home to my office, the average speed is 40 kilometer per hour. Now, do I drive absolutely with a constant speed of 40 kilometer per hour all the time? No, I obviously do not. There are traffic signals where I stop, so at the traffic signals I'm not moving at all, so my speedometer needle indicates 0 there. There is a long sort of expressway from in a part of the distance from my home to my office. There's a 5 kilometer flyover where there are no traffic signals. So that 5 kilometer distance I generally cover very, very rapidly, traveling almost at maybe 80 kilometer per hour. I hope no traffic inspectors are watching this, but I generally make this in no time at all, traveling at 80 kilometer per hour, at times perhaps even more. And eventually, when I get close to the office, there are lots of turns and that I have to take, and therefore I slow down significantly when the turns are happening, and the speedometer needle has a different reading all the time, which means that the average speed is representative of the motion as a whole, but it does not tell you what is the rate at which an object travels at a given point of time. Now what the speedometer needle indicates is the speed at a given instant. And therefore we will now look at what is the velocity during an instant or at an instant. Now an instant by definition involves an interval of 0 time, and if we take 0 time, the displacement is 0, and if we divide 0 displacement by 0 time, we have a 0 by 0, which is something that even mathematicians cannot really handle. They say it is an indeterminate quantity. Now to get around the problem, we use differentiation, and by that what I mean is, instead of taking 0 time, we take a small amount of time, a very, very, very small amount of time, which we represent by dt. Now this dt is a really, really small amount of time, which is very nearly 0 but not 0. Now in this very tiny amount of time, the object undergoes a displacement dx. And if we now divide this dx by dt, we get instantaneous velocity at a given instant. So the instantaneous velocity during a motion is dx by dt, and for the same instantaneous calculation, the speed or the instantaneous speed ends up being the magnitude of this quantity. Now instantaneous speed will always have a magnitude equal to instantaneous velocity. The only difference will be that instantaneous velocity will always be expressed with a sign which will be positive or negative, indicating positive or negative x-axis direction of motion, whereas with speed there will be no sign, because when we express speed, we just express how fast an object is traveling without really bothering about the direction. So speed, instantaneous speed, is a scalar. We do not bother with direction here, so we do not have to show a sign, and therefore it's a mod, whereas instantaneous velocity has a direction in addition to a magnitude, so we always express it with a sign. These were the definitions of some quantities that we will be using in describing motion.